First example, on the right-hand map, this was a map that was published by Cienzano early in days, that was showing the number of cases at the municipality level. And then there were the questions, why are there more cases in Flanders? And, from an epidemiologist point of view, the answer is obvious. It's simply because, human population density is much higher. So even if you had an equal incidence everywhere, you would have more cases in Flanders. So, I spent the time of putting those maps together to explain that. But it is something that from an epidemiologist's point of view is completely obvious, but certainly not to all the peoples who receive those different pieces of information. And all of those pieces of information are shared through the media, are shown every day, etc. A second very important element is there is a little understanding in the public and in policymakers of the difference there is between what is observable and the true epidemic. So this is, and this implicit what we call epidemiological pyramids, where we know that there are more asymptomatic people than there are mild cases, and that there are more mild cases than severe cases, and that there are more severe cases than death, is something that as epidemiologists or medical scientists we know, but not everyone is aware of that. So of course, when the case definition during the first wave only include death and severe cases, it was a very small subset of the true extent of the epidemic in the real world. And then the case definition changed early May to include mild cases that were detected for general practitioners. And then the case definition was changed early June to include at-risk contacts that were identified for contact tracing. But of course, the fact that people or policymakers or some of the media didn't know that those were, in fact, that the case definition changed, meant that people couldn't understand this left-hand plot. So this left-hand plot is how this changed over time. And of course, knowing that the case definition changed, as medical scientists or as epidemiologists, we know that what we see on the right-hand part of the plot doesn't represent the same thing as the left-hand side of the plot. But for the public, but even for policymakers, that's not obvious at all. They don't know that until someone explains clearly what's happening behind. So what they see is that, and then they start calling medical scientists fear-mongers, you're spreading fears because, in fact, there's no one in hospitals, etc., etc. This is just because there's a misunderstanding there. And that's why at that stage, communicating through the curve of hospitalization was somehow more effective, because it was something that was more stable over time. Another element is that there's very low familiarity in the public in general with numbers and with the nature of contagion and what is an exponential growth. And I find this visual really, really helpful in that. It simply shows, on the chessboard, what's the consequence of doubling the number of rice grain as you move from one box to the next. When you're familiar with numbers, this is obvious to you. But if you're not, this is not something you can materialize mentally. It goes against the cognitive bias. That, yeah, okay, in the first 3 cases, we all good, yeah. And then on the next 4 or 5, yeah, then it's becoming serious. And then very quickly, it becomes completely unmanageable. And that's exactly what we're seeing now in hospitalization. But until you have that in the back of your mind, when you have only a few rice grains, you think we're all safe. And this is another visualization of that same principle. If you don't realize the nature of what a chain reaction of an exponential growth, you cannot understand why early action is so beneficial. And this visualization, I find it very useful. It shows, you know, if you have a chain of transmission, if you break a few of the transmission events early in the transmission chain, well, it has a massive implication much later on. So where is it best to act? On the left or on the right? I mean, clearly, when you see it in this way, the answer is obvious. But when we were trying to convince people during the summer that we had to maintain prevention, the main message back was saying, you know, it is unbalanced. You know, we cannot afford that. We have to balance life, etc., without considering that what we would have done in the summer would in fact prevent a much larger number of cases much later on. And that's simply because people don't have in their mind the nature of exponential growth and of a contagious process. And then you get all kind of criticisms, depending on how you present the data. This is, I was trying to convey this information through those plots at some point. So I was using plots that had a log scale on the y-axis. And then I was to try to show so that people could see where we would be if the trend would continue. And I was criticized for minimizing the problem by using a log scale. And then someone else was using, and that's Nicolas van der Waal, who's been publishing tweets with plots, etc. He's not using a log scale, he's using a standard scale. But then people complain, we didn't see it coming. We were taken up by speed, because it's more difficult, in fact, to extrapolate mentally an exponential growth on this type of scale. So there's no good way of presenting the information. It's just two ways of presenting the same type of information. But it's difficult to translate this message into a proper understanding of what it represents. Then there is what I call the confusion between speed and acceleration. So here on the left-hand side, you have, this is the number of the daily new cases per 100,000 people. It's average. And then you have the first wave, and then you have the situation as it was in July and August. So the speed is the number of cases per day. It has a unit of speed. It's the number of particular events over time. What I call acceleration is the growth in cases per day. And it's in fact the derivative of those events per day. So it's in fact, it's the slope of those lines here. So if you fit those growth with a curve, the slope gives you the acceleration. It's positive when things are growing. It is equal to 0 when things are stable, and it is negative where the speed, the number of cases is declining. And what people don't realize is that everything we do in society as prevention has an impact on the acceleration, but not on the speed. And that's quite essential for the following reason. Hold on, because why does it matter? Imagine this is a plot of the number of deaths per day over time. And one objective could be, okay, let's keep the number of deaths as low as possible. And then someone else comes and say, you know, those measures you're recommending, the societal cost is too high. You're asking people to do too much. We cannot live like that forever. You know, we must accept that it is causing a number of deaths, like flu deaths, etc. Fine. We could say as a society, let's accept a higher number of deaths per day. But the thing is that in both cases, it means that even if you want to stabilize your epidemic at a later stage, it means that you have to bring your acceleration to zero. You have to make it horizontal. So it means that your growth rate should be equal to 1. And the thing is that in order to do that, the measures that you're going to need to implement for your society, like closing bars or limiting the number of contacts or all of those measures, they will be identical if you are up here or if you are down here. They're independent because it's only through those combined measures that you can keep things stable. So why letting things go to a high level if by the end of the day you need to implement the measures anyway? You're ending up in a lose-lose situation because you have to implement the measures anyway. They have their economic costs, and yet you have more death and morbidity. And that's confusion between speed and acceleration is also something that has been, that has made the prevention message very difficult to convey to lots of people and policymakers as well. There's also no familiarity with the basic notions of sampling. This is an example. This is a plot that is in the daily Cienzano report. It shows the proportion of positives in the set of people who are sampled. And I showed this plot to some of my students, and I asked them, tell me, if let's say that the positivity ratio is 15% per day in the set of people who were tested, who are sick people, their contacts or their high-risk contacts or returning travelers. And then I asked, if you crossed 100 people in the streets last week, how many positive do you think you've crossed? And the most common answer was 12.7. They didn't have this immediate perception that this is not a representative sample of the entire population. So this positivity ratio does not represent the proportion of people who are infected in the streets. It's the proportion of people who are infected in those who are tested, and it's a different thing. But it is by no way intuitive for people who don't have those notions of sampling. And in all the different interactions I've had with policymakers, and that's very important and a very important message, they were convinced and they tend to believe things that they could understand. And for example, the reproductive number RT, the effective reproduction number, which is a concept that is widely accepted among epidemiologists because it's a useful indicator, is something we've had lots of difficulty communicating about. Because we've had this discussion. We were saying, RT is a very simple thing. It's the average number of people infected by each infected person. And then you would have one of the politicians ask, yeah, okay, interesting. How do you calculate it? And then of course it's a bit complicated, and then there are a few assumptions, and you're forced to admit that. And then they start becoming suspicious, and they say, yeah, okay, because it's something that they find problems manipulating. And we had exactly the same problems with trying to convey the messages that go with predictive models. There's a big misunderstanding on the nature of predictive modeling in the course of an epidemic. Now, all those simulation models, their value is not to predict the future, because the future is so much influenced by what people will actually do of your preventive message, that the future is by nature quite unpredictable. But they're very, very useful to try to measure what could be the possible effect of different scenarios So what if we reduce contact in this particular domain? What if we reduce contact in school? What if we reduce contact in HoReCa, etc.? Those kinds of applications are useful. But when you present this to a lay audience, most of the time they would think that you're making actual predictions, that you believe that this is going to be the future as you would do in meteorological forecasts, which is absolutely not what those models aim to achieve. And then comes another big challenge, and it is to be publicly challenged by what we call armchair epidemiologists, who get a few facts here and there, and then or make their own observation to make bold statements such as this is not worse than the flu, and then of course you have to bring in lots of studies and put them together to be able to respond to those claims in an effective way and try to convince. And some people remain unconvinced by even when you bring in evidences. Or we've had other armchair epidemiologists who were, putting very, very scary models, and sharing them, and then the press would pick them from a Facebook post. And this is an example. I mean, it was a Facebook post by a professor of biostatistics who was simply keeping the growth rate at 1.2. And of course, if you keep that, you're predicting a big wave. But this model is far more simplistic to generate any useful prediction. And then, of course, it gets picked by the media or by policymakers, and then you're being called fearmongers, etc. Or you also have some other armchair epidemiologists, who publishing opinion papers such as this one, suggesting essentially people are lying to you, and sometimes in a very, very harsh way. This was a one opinion paper by an engineer, and who was blaming Cienzano for being intellectually dishonest, and with a very, very harsh title. And when in fact Cienzano they had simply been using in one of their press conferences one of the model of a true group of epidemiologists, but of course they didn't communicate it in the same way with all the sets of precautionary comments that surround and around uncertainties and all of that. And of course it was a completely unfair criticism. So how to address all those challenges, and that's what is made difficult. So my take on that, out of those different experiments, is first try to work on the basis of observables or indicators that everyone can have access to. Try to work with facts. Try to work with things that speak to everyone and that are relatively constant over time and region. Second one was to try to use simple indicators that everyone can calculate, and that everyone can verify by themselves that what you're saying is what they can observe themselves too, if they redo the calculation. Have one indicator for speed and one for acceleration, for the reasons I outlined before, because both needed to be communicated simultaneously. Use very simple models for projections, models that people can understand and communicate about uncertainties. So we try to put this in what has been the initial barometer. So this is an exclusive view of what we have been putting together as our barometer. So on the top left diagram, you have the incidence in cases over 100,000 people, and how it has evolved over time. And on the bottom left plot, you have the incidence of new hospitalization per 100,000 people. So that's your two measures of speed. And then we produced two measures of acceleration. One that is the case daily ratio, and the other one that is the reproduction number. So we use both because reproduction number has this limitation that it cannot be calculated easily. So the case daily ratio is an estimate of by which number do you need to multiply the number of the day before to have the number of today. Or in other words, by which number do you need to multiply the number of cases you've had today to get the number of cases you're going to have tomorrow. And at the moment in Belgium for cases it's 1.1 and for hospitalization it's 1.11. And it's relatively straightforward to estimate. You just take your last 14 days of data, you log transform it, because the fact that you are log transforming linearize the relationship in terms of degrowth or growth. And then you apply a linear regression, you take the slope of that regression, and then you back transform that. And that gives you that number. So it's something that is very easy to calculate. And of course, you can use the projected value out of your linear regression to get the projected value into 1 week or 2 weeks if the trend continues exactly as being the same as the one you had in the last week or 14 days. And that's exactly what we did. So this is the visualization for Belgium. And this is what you have for cases. So this is the present situation for Belgium and for different provinces. And the bar give you the present time incidence per 100,000 people for over 14 days. And then you have the black dots that tell you what are the projected values within a week time if the growth remain identical in the next 7 days as it was in the last 14 days. So that's the projection over the next 7 days. This is the projection over the next 14
pour avoir
days.
du son plus fort, c'est là. Pour avoir un écran mieux éclairé, c'est le petit soleil.
C'est parfait.
And this is the same for hospitalization. So this is the present state of hospitalization incidence. And the dotted line here is where we were at the peak of the first wave. We can see that Belgium as a whole is here on the top. The 7 days projection is still below where we were at the peak of the first wave. But if we maintain the growth rate we've had in the last 14 days for the next 14 days, we're going to be over that in 14 days. And that's essentially as simple as that. So it gives where we are now and where we might be in the future under the current regime. And finally, maybe a last two concluding points out of the many interactions we've had. We should never underestimate the weight of the personal experience of people we speak to, whether it is public or whether it is decision makers. Many times, you present evidence collected statistically with all the kind of robustness you're trying to put around it. And then in one of the meetings, one of the policemen say, yeah, but you know, I talked to the guy who's in my hospital next door, and he said things are fine. And that's it is his personal experience. But his personal experience influences his point of view in the decision that is going to be taken. And it takes a lot of energy and effort to convince people who have a different personal experience that what they have perceived locally in their neighborhood, through their social networks, through their friends, through their contacts, is not what is generalizable at the population level. And finally, if there's one big message, we should give crash course in epidemiology to decision makers, because frankly, it would have prevented a huge amount of misunderstanding through this through all those different months. And with it, I'm at the end of this talk. Thank you.
So thank you very much. I think it's really a very useful presentation to spread what we learned from you to our colleagues, family and friends, and to back over our personal experience, but also to have given us real indicators that will help us. Of course, there might be a frustration during this, what we can call second wave, or we never had a flat, a flat sea. Are there any questions in the room? Who's that? Yes, there is a question from Charlotte Martin. We know from vaccine hesitancy experience that we have a problem in health literacy in Belgium, and we are now paying a costly price for that. In the coming years, we have to tackle this problem quickly, beginning in fundamental schools, in my opinion. Could you hear me? Oh.
Voilà. Il y a un crétin qui est en train de partager.
This is funny.
Congratulations, Bob.
No, I agree. There is lots of similarities between some of the reactions we've had to recommendations in terms of preventive measures. There's lots of similarities between that and the vaccine hesitancy, with accusations of conflict of interests, of the fact that the cure might be worse than the disease, etc. So it is certainly something that can be tackled simultaneously, and even preventively. We could start thinking of doing some work with the schools, and I think it would be a really good idea. Yeah.
Another question. So all the auditors, thank you very much with your enlightening presentation, and of course it will be shared. All the presentation will be shared. Is that? If you had the opportunity to change one thing in Cienzano policy, what would it be? Big question.
It's a big question, but I think they really need to have a culture shift in terms of how they work in their partnership with academia in general, and in their in terms of open data policy. I mean, I think it's no longer acceptable from a societal point of view that some useful data are being not accessible to a wide sets of experienced scientists with such strict conditions. There should be the recognition that this is public data for a public problem, and that it would only serve society as a whole if things were made easier in that regard, especially when we do have to deal with a real-time problem.
Okay, thank you very much. Is it planned in the near future for the crash courses to policymakers?
No, it hasn't been planned, but this is certainly something that no one of my epidemiologist colleagues would contradict me, and they'll probably be happy to.
Okay, and the last question before going to the next session: how do you determine death rate in COVID? So many people asymptomatic are not tested.
Yeah, that's an excellent question. I mean, it's the limitation of all estimates of infectious fatality rates that have been published. I mean, there's always this limitation that you may be missing some of the infected people in your denominator. But the thing is that even in countries where they have implemented really, really massive testing, the figures were converging. Like in South Korea, they had at some time been, testing massively, and still they had the 0.7% IFR. Also on this boat, you remember very early in the epidemic, there was this crusade boat. I think it was the Diamond Princess, and within that boat, I think almost all of the people were tested, and even then, the value of the infectious fatality rate was quite consistent with the other numbers. So there's still always the possibility that we might be missing some people in the denominator, but there's been so much convergence in those different estimates that have been done that I think that they are becoming quite reliable now.
Okay, thank you very much for your time, for really the very useful presentation, and try to